Hallmark solution 4.2, a 180 kVA, 381 volt, 50 hertz, 6-pole, 3-phase generator has an effective armature resistance of 0.016 ohms and an armature leakage reactance of 0.07 ohms per phase. Determine the RPM of the prime mover necessary to deliver rated frequency. Compute the excitation voltage when the generator is delivering power and voltage at a load power factor of unity, 0.7 lagging, and 0.7 leading. The givens in this problem are that the magnitude of the three-phase power is 180 kilovolts, right? Generator ratings are given on a three-phase basis, so that's all three phases, 180 kV. We know that when terminal voltage is given, it's actually given on a line-to-line value, so the magnitude of the terminal voltage is 381 divided by the square root of 3 volts. That converts from a line to a phase voltage. We're told that 50 hertz, that tells us the electrical frequency of the system. Poles is the number of magnetic poles in the generator. It's given the symbol capital P. Armature resistance, the symbol for armature resistance is R sub A, 0.016 ohms. And we've got a leakage reactance of 0.07 ohms per phase. Since that's the only thing specified in terms of a reactance, that is X sub S is equal to 0.07 ohms. I think more technically that's X phase plus X sub A, but since that's the only one specified, combine that all together, it becomes the synchronous reactance of the generator. So what are we asked to find? That is the mechanical rate of rotation, as we saw in example 1, that is given the symbol N sub M for mechanical rate of rotation. That's to deliver that 50 hertz. And then we're asked to determine the excitation voltage. And so the question is, well, what's the excitation voltage? That's EF. So under those different conditions, we're asked to find EF. So the solution in part A, we just need to return to the fact that the mechanical rate of rotation is equal to the electrical frequency times 120 divided by the number of poles in the generator. And so that tells us that the mechanical rate of rotation is equal to 50 hertz times 120 divided by the 6 poles is equal to 1,000 rotations per minute. So that's the mechanical rate of rotation to achieve the 50 hertz rated frequency in this system. So that's part A. Part B is determine the excitation voltage for rated power and voltage at a load power factor of unity, 0.7 lagging, 0.7 leading. So to do that, what we want to look at is how the different loads change the phasor diagram for the loaded generator. So I'm going to start just by drawing the circuit model for the generator. We've got the excitation voltage E sub F that is induced in the armature coil. We then have the armature resistance and the synchronous reactance of the armature X sub S. The output voltage after the voltage drop associated with the current flow through those two devices is called the terminal voltage VT, and that then serves this load ZL. So that's the circuit diagram. We have a couple different phasor diagrams depending on the relationship between IA and VT, and VT is taken as the reference phasor for all of these analyses. So if we look at this circuit model, we have the governing equation that the excitation voltage EF is going to be equal to the terminal voltage VT plus the voltage drop across RA plus the voltage drop across XS. So that's Kirchhoff's voltage law, and if we use Ohm's law, we can write that as EF is equal to VT plus IA times RA plus J times the synchronous reactance. And this is usually the formula you'll use to solve these problems. That one right there comes from this one, though, which you can easily take from the circuit model. So what we're looking at here is for a power factor of 1 at rated terminal voltage. What we need to do to solve this problem is we were given VT because we were told that the generator is supplying rated current or rated voltage, excuse me. We know RA and JX as we're given in the problem statements. We don't know IA, so we have to determine what the rated current is from the rated voltage and rated power. The relationship there is going to be that S on a per phase basis is equal to IA star times the terminal voltage, right? The power delivered by this pair of terminals is equal to the current flowing out of it times the voltage across the terminals. So power was given to us on a per phase basis, and that's 180, or sorry, on a three-phase basis, so that was 180 kVA. If I divide that by 3, I get single phase power. This is a power factor of 1, which means that the angle associated with that is 0 degrees. So that's that. And then we say is equal to IA, and then VT was given to us in the problem statement as 381 over root 3. At angle 0 degrees. And so if you solve that, you get a current of 272.764 at an angle of 0 degrees amps. So that's the rated current at a power factor of 1, which is, that's where that angle came from. Power factor is equal to 1 right there. So now what we can do is we can plug all our numbers into the equation for the excitation voltage. Excitation voltage is going to be equal to 381 over root 3, angle 0 degrees, plus 272.764, angle 0 degrees, times 0.016, which was the armature resistance, plus J 0.07, the synchronous reactance of the armature. And let's see, so this, just to give you a sense, this times this is the voltage drop across the resistor, and this times this is the voltage drop across the inductor. So you don't have to do those individually, but I just want to show what some of those magnitudes. The voltage drop associated with that internal resistance of the armature is about 4.36 at an angle 0 degrees volts, and the voltage drop across the synchronous reactance of the armature, VXS, is going to be 19.09 at an angle of 90 degrees volts. Again, you don't need to do those separately, but just thought you might be interested in seeing what those magnitudes and angles were. So anyway, we add those together and you get a excitation voltage of 225.146 at an angle of 4.87 degrees volts. So if I've got a rated load and it's a unity power factor and I want to deliver it at rated voltage, what I have to do is I have to set the excitation voltage to 225.14. And that'll actually take care of the angle 4.87 itself. So in part 2 here of section B, we've got a lagging power factor. So I'm just going to draw a phasor diagram for a general lagging power factor. Remember, we've got the terminal voltage is our reference here. We've got IA right here. We've got the voltage drop across the resistor has to be in phase with that current, and then 90 degrees out of phase with the current, and therefore with this voltage is the voltage drop across the synchronous reactance. And then we've got EF. The angle between EF and VT is called the power angle, delta, and the angle between VT and IA is called the power factor angle, phi. So we were told that this was a 0.7 power factor lagging system, so I'm going to just go ahead and solve for phi. That's equal to inverse cosine of 0.7, and that's 45.573 degrees, gives us our power factor angle. We're going to use the same formula as we did up here to solve for this circuit. So again, I have to solve for IA. IA is going to change because my power factor's changed. So to do that, not wanting to scroll. There we go. IA won't set up the equation because you already saw it, but it's going to be the complex conjugate of 180 over 3. The angle is going to change in this calculation. 45.573 degrees. But the voltage doesn't change, it's still 381 over root 3. And then I take the complex conjugate of that, and I get 272.764 at an angle of negative 45.573 degrees. So that is the current. We can see that all it did was change the angle of the current as compared to the previous calculation. And now we can plug that into our calculation for the excitation voltage. That's going to be Vt plus the current times the synchronous impedance of the generator, which again was 0.016 plus J 0.07. And so we get an excitation voltage in the lagging case, rated power at 0.7 lagging, of 236.883 angle 2.48 degrees volts. So we can see that we actually, to provide the lagging, same amount of current, but at a lagging power factor of 0.7 instead of unity, we actually had to increase the field voltage, or the excitation voltage, excuse me. We had to increase the excitation voltage by about 10 volts. So that's part 2. Part 3 asked us to repeat this for a 0.7 leading system. And so just to remind you what that looks like, we've got Vt, the terminal voltage is always our reference. A leading current is going to be in the first quadrant, so that's IA, and that is the power factor angle right there. The voltage drop across the resistor in that circuit model, that there, is in phase with the current, so that points that direction. And then the voltage drop across the synchronous reactance is 90 degrees out of phase with that, so that's that direction. And EF is that guy right there, so that's EF, that's the power angle, that's the voltage drop across the synchronous inductance, VXS, and that's the voltage drop across the armature resistance, VRA. We already showed that the current, all it's going to do is change angles. So for a power factor leading of 0.7, we're going to get IA is equal to 272.764, angle 45.573 degrees. Should be right in units on here, amps. So you can save yourself some time, since you know that it's still delivering a rated current. It's just the power factor's changed. So that's lagging, this is leading. And so now we can real quickly calculate the excitation voltage, which is just going to be 381 over root 3, angle 0, plus this current, 272.764 at an angle of 45.573. We need to multiply that by the synchronous impedance, 0.016 plus J 0.07 ohms, and you get a excitation voltage of 210.038 at angle of 4.5 degrees volts for EF. So as you can see, the excitation voltage that we calculated in this situation is reduced as compared to the leading category. So that's interesting. I think maybe more interesting is what is, right, EF is this, resistance, reactance, we've got those, terminal voltage, EF, and I've been using 381 over root 3 for this value right here. So 381 over root 3, if you do that math, that's about 220 volts. It's approximately 220 volts. So we see that for a leading power factor, the excitation voltage is actually lower than the terminal voltage due to the phasor mathematics, which is very interesting. Leading power factors, or positive Q's on the load, actually cause the terminal voltage to rise on a synchronous generator. Very interesting phenomenon that isn't immediately obvious, I think.